All right, an electrode has a negative electrode potential. So that's on the table that we were looking at last class. Which statement of these is true regarding the potential energy of an electron at this electrode? Does the electron have lower potential energy than at the standard hydrogen electrode? Does it have a higher potential energy than at the standard hydrogen electrode? Or does it have the same energy as at the standard hydrogen electrode? Yes? We've got a guess for A, we've got a guess for B. So our standard electrode potentials are written in the reduction form. So lithium was the one on the bottom. It has like a -3 something value, very low. That means that it is very unlikely to occur, really is not going to occur in this direction relative to the hydrogen electrode. It is very likely, though, to go in the other direction. So lithium going to lithium plus E minus would have then a +3, meaning that it really wants to give up an electron. And so it has a higher potential energy. It has a really strong electromotive force to push it away just practically anywhere else. So this one's going to be B. It's a higher potential energy. Remember that these numbers are voltage numbers, and voltage is like the steepness of a stream. So on a relatively flat stream, it'll just kind of meander. If you take it to the extreme and you have it almost vertical, then you've got a waterfall. That's going to be a lot of potential. That water is going to fall. So a negative electrode potential, the electrons at that electrode would have a very high potential energy compared to our standard hydrogen electrode. We can predict spontaneous direction for an oxidation-reduction reaction. So we're going to compare our standard cell potential for each of our half reactions. The more negative cell potential tends to lose electrons. Oxidation is loss of electrons, and reduction is gain of electrons. That's going to be our more positive. Standard cell potential. So cell potentials, at least in the table that we have, are written as reduction half reactions. And positive is spontaneous, spont. Negative is non-spont. It's not going to happen as written. For any spontaneous reaction, our standard cell potential should be positive. If you don't want to think about it this way, then a rule that you can memorize: any reduction half reaction is spontaneous when paired with the reverse of one below it. And this gives a positive standard cell potential. All right, an example. We've got nickel 2 plus 2 electrons going to nickel metal, and then we've got one for manganese as well. If we want to make this a spontaneous reaction, what do? We have to flip one of them. So our memorizing rule, without thinking about cell potentials, any reduction half reaction is spontaneous when paired with the reverse of one below it. So we'll reverse this manganese one. So manganese metal going to manganese 2 plus ion plus 2 electrons. And since we flipped it left and right, our standard cell potential also flips. So it's now positive 1.18 volts. And if we combine this half reaction with the nickel half reaction as written, it turns into this. And our cell potential is going to be negative 0.23 volts plus 1.18 volts. The thing that I omitted from writing this out, and what we're typically going to see omitted, is the number of electrons. In this case, from our reduction half reactions, we've got 2 electrons for both, so we know that they're going to cancel out if we just keep them as whatever the coefficients they had before are. Sometimes we'll have to do some multiplication to get those electrons to cancel out. Okay, so our voltage should be 0.95, or our standard cell potential should be 0.95. And that's what our galvanic cell or voltaic cell would look like. So our manganese is our anode. Anode is where oxidation occurs. Oxidation is losing electrons. Manganese, to get us a positive cell potential, is now written in the oxidation form. So manganese is doing oxidation here. It's losing these 2 electrons. That makes it our anode. Those electrons are flowing to the nickel. Nickel is still in the reduction half reaction. Red cathode. Reduction goes with the cathode. Alternatively, I suppose you could just remember that the top one, if they're in the table, the top one is the cathode and the bottom one is the anode. That would probably also work. Questions?
And did you just reverse the 1 to get like a positive on each side? Or?
Yeah, I reversed the 1 so I reversed the manganese one because our rule of thumb from this previous slide, any reduction half reaction, we have reduction half reactions, is going to be spontaneous when it's paired with the reverse of 1 below it. So these are in the order that we would see them on the table. So if we reverse this bottom one, that changes the E cell, or the standard electrode potential, to a positive, and then we get an overall positive cell potential. And some of the numbers that I had written there disappeared. That was a 3. This was a 5. So yes, the goal is to get a positive cell potential for these galvanic or voltaic cells, the batteries. Okay, without calculating the standard cell potential, predict whether the redox reaction that's listed here, that's this one, zinc and nickel, is spontaneous. Sketch the electrochemical cell in which the spontaneous reaction would occur, label the anode on the left, the cathode on the right, and the direction of electron flow. And I'll give you a little bit of time to do that. All right, we have zinc and zinc ion. We also have nickel 2 ion and nickel. Some of our transition metals, many of our transition metals show up multiple times, so it's important that we pick the correct half reaction. So our nickel 2 plus, is here, and our zinc is there in red. Looks like nickel and zinc are not ones that show up twice, thankfully. So we first want to figure out whether it's spontaneous. What's our rule for something being spontaneous if we don't want to look at cell potential? We flip one of them, and it'll be spontaneous. Which one do we flip, the top one or the bottom one? The bottom one. So if we have a reaction paired with the flipped version of something that's below it, then that will be spontaneous. And right, this is the zinc. This is below nickel on our reduction half reaction thing. And so if we flip this one, which is what we have here, then it will be spontaneous. Okay, so this will be spontaneous. Another way that we can think about it is that we can see that we've got our standard hydrogen electrode on the top. Everything that's below it is going to have a negative cell potential, and the further down we get, the more negative that cell potential is going to get. So let's say that our nickel was like 0.5 and our zinc was negative 0.75, right? Negative 0.5, negative 0.75. If we flip the negative 0.75, it becomes positive 0.75. Then we've got 0.75 minus 0.5, we'd end up with a positive 0.25. Those aren't the actual numbers, but that's like an example of knowing the trend, what we could do with it if we really wanted to think about it in terms of cell potential. And then we want to sketch the electrochemical cell. And this is where my lack of training as an artist really shines. Okay, we've got electrodes. We also will draw a salt bridge just for fun. It's not really important that you draw the solutions. The salt bridge needs to go into the solutions though. And then we also need a wire. Okay, so that's our wire. We've got electrons flowing in the wire. We want our anode on the left. And our cathode on the right. Just knowing that we have our anode on the left and our cathode on the right, which direction are the electrons flowing? What's happening at the anode? Oxidation or reduction? Oxidation, and what is oxidation? Losing electrons. So electrons are going from the anode to the cathode. So oxidation is losing. Electrons flow from the anode. And then we have to think about, in our chemical reaction, which of these is undergoing oxidation. It's not nickel. So nickel is going from 2 plus to neutral. Its charge is decreasing, meaning it's picking up electrons. So nickel is gaining electrons. So nickel is doing the reduction here. Nickel 2 plus to nickel is reduction. So our cathode is nickel. Reduction happens at the cathode. Our anode is the one that's losing electrons. Zinc is giving electrons to the nickels, so zinc is losing electrons. And zinc is our anode. And then we would have some solution with these metals dissolved on their respective sides. We'd have zinc dissolved in the solution on the left, nickel dissolved in the solution on the right. We would have some strong electrolyte solution that's in our salt bridge, but we weren't asked to provide that here. Any questions? All right, is the following redox reaction spontaneous under standard conditions? We've got zinc going to zinc ion. So that's going to be this reaction. And we've got calcium ion going to calcium metal. Which one of those two, which of these two reduction half reactions did we flip to make this? Zinc. So the top one is flipped. The one that's above is flipped. And our rule for a spontaneous one is that the bottom one is flipped. If we flip the top one, it's not spontaneous. So that would be the simplest, we've got our one rule that we memorized. That would be the simplest way of doing it. We could also think about it in terms of the cell potential if we wanted to. I'm not going to. All right, another one. Let's say that we've got a solution that contains both sodium iodide and sodium bromide. Which oxidizing agent could you add to selectively oxidize I- but not Br-? Our options are chlorine gas, H2O2, copper 2 chloride, and nitric acid. And I think the trickiest part of this problem is finding all four of those things. The other part that we need to think about is what does it mean to oxidize I-? What does it mean to oxidize Br-? What's happening to the I- or the Br- when we oxidize it? They're losing the electrons. So since we want to oxidize just the iodide, we want it to lose electrons. We're looking for something that looks sort of like I- going to I plus E-. It's actually going to be 2I- going to I2 plus 2 electrons. So we're looking for something that looks like that. And that's down here, but flipped. So there's our iodide one. it's written here in the opposite direction. Right, from the oxidation, it's written in the reduction part. So we've got this one flipped. So this will be spontaneous paired with something above it or below it, since this one is flipped. Above it. So since this one is the one that's flipped, we're looking for something that's above that'll be spontaneous. It's going to be the same idea for Br minus. So our Br minus reaction is up there with the green. If it's above this Br minus, this one is also flipped if we're oxidizing it. So this one's flipped. So if we have something above that, it'll also oxidize the bromide. So what we're looking for is something between these two. So this blue region, this is where we could find something that would oxidize the iodide, but not the bromide. Do we see anything in there that looks like any of our options? We've got the H2O2. Right, our H2O2 is there. If we have H2O2 in solution, or if we add H2O2, is this written the correct way to oxidize I minus? Or is it flipped? It's flipped. So the H2O2 one is flipped. It's not H2O2. It is the HNO3. And this is why I was saying that this is arguably the trickiest part. The HNO3 is disguised here as H plus and NO3 minus. So this bit here, this is our HNO3, reduction half reaction. And the reason that it's like all broken up and weird like that is to get it to balance out. So that's the correct answer. Questions other than why is it all weird like that? All right, so that example is helpful. It's related to predicting whether a metal will dissolve in acid. So generally, acids dissolve metals by reduction of H plus into H2 gas. That's our standard hydrogen electrode, half reaction. And if we combine that with an oxidation half reaction for zinc, then that gives us this this full redox reaction. So oxidation paired with our standard hydrogen electrode. Our rule of thumb, our memorizing rule, is that metals with their half reactions listed below the reduction of H plus to H2 will dissolve in acids. So our standard hydrogen electrode is listed, kind of in the middle of our table. Anything that's below that flipped, right, will be spontaneous. So any metal that shows up below our standard hydrogen electrode will dissolve in metal. In acid, sorry. Will dissolve in acid, not dissolve in metal. Might also dissolve in metal, but. And there's one important exception. So we've got one special acid that we'll talk about. Nitric acid, the HNO3 that we broke apart and looked really funky on the table, it's got a positive value for its cell potential. So that means that it's above our standard hydrogen electrode. And so this can be used to oxidize things, oxidize metals that are above our standard hydrogen electrode on our table. So nitric acid can dissolve metals above the standard hydrogen electrode on the reduction table. Or the standard cell potential table. Okay, and here's a look at doing this. Our standard hydrogen electrode would be at the very bottom of this table. So we want to pick which one of these metals will dissolve in nitric acid, but not in HCl. So our options are iron, gold, silver. So the first place that we should start, the place that I would recommend we start, is finding our nitric acid. It's our weird disassembled HNO3. And we're looking for something that's below our HNO3 on our table. And we're looking for these with the solid tag. So gold is way up here on our table. That won't dissolve in nitric acid or in HCl, so it's not gold. Where does iron show up on this table? But it's aqueous, right? So iron shows up, but only as aqueous. So this is not Fe. It's a solid. That's actually below H2 on our table. The correct option here is silver. Silver shows up 2 lines below, and it's silver as a solid. So if we flip that direction, if we flip this half reaction, right, we'll have silver on the left going to silver ion on the right. That's the way that it dissolves. And it's below our nitric acid, so that will be spontaneous. So some of the concepts that we've been talking about, like in the last chapter, couple chapters, actually relate to our cell potential. For spontaneous redox reactions, our delta G, our standard change in free energy, if that's negative, that's a spontaneous reaction. If our standard cell potential is positive, that's a spontaneous redox reaction. And if K is greater than 1, that is also going to be a spontaneous redox reaction. So this whole bit might be helpful to have memorized. And we can relate all 3 of these concepts to each other. So we'll be going through each of those arrows we'll start off with our relationship between standard change in Gibbs free energy and standard cell potential. So our potential difference is the maximum amount of work that we can get out per unit charge. Our energy is joules per coulomb. We can rewrite this as energy is the maximum work over Q, and then we can rearrange that. The maximum work done by the system, that's why we have a negative number here. So the maximum work that the system can do, it can lose this much amount of work, the charge times the cell potential. And you may remember Gibbs free energy is the maximum available work. It's the maximum amount of energy that we could possibly get out of the system to do work. So we're excluding the heat loss that we might experience. We also get a new constant, and this new constant is Faraday's constant, F. So Faraday's constant, F, here is the charge of 1 mole of electrons. That's all that is. I think people are on the roof. So our total charge in any reaction is going to be Q, and that's going to be the number of moles of electrons times Faraday's constant. So just giving us this charge value. So moles of electrons in the balanced equation. Basically just what's the coefficient on electrons. So we can substitute that into our Wmax equation. And since the standard free energy is the maximum amount of work, like I mentioned earlier, we can trade out standard change in free energy with Wmax, or work max. And so we get this very helpful, very important equation. Again, keeping in mind that this n is the coefficient on electrons in the equation. Sometimes it'll be 1, sometimes it'll be 2, it might be 6, it might be some other number. And then F is Faraday's constant, and the standard cell potential we can calculate or look up. Okay, so we're going to need Faraday's constant, 96,485. (96,485) coulombs per mole of electrons. Delta G is negative NFE. Okay, using tabulated electrode potentials, let's calculate the standard change in Gibbs free energy and figure out if the reaction is spontaneous. So we have sodium and H2O. We've got H2, we've got OH minus. We need to find our reduction half reactions. So we've got H2O with H2 and 2OH. That's going to be down here. Right, there's our half reaction. It's got H2 on the left, or H2O on the left. It's got H2 on the right. It's got O2 also on the right. So that's our first reduction half reaction. Our other half reaction is sodium and sodium ion. We've got sodium down here. That one is flipped. It's also doubled. We don't change anything about the cell potential for changing the coefficients. So the first thing I propose that we find is the standard cell potential. I don't think there's a delta. Our standard cell potential is standard cell potential of, I think it's the cathode first, minus the anode. It's a very unhappy face. So this is our formal equation. What does it mean to be an anode? What's happening at the anode? Oxidation or reduction? Oxidation. Oxidation is what of electrons? Yeah, so it's losing electrons. Which of these two is losing electrons? Is the sodium losing electrons or is the H2O losing electrons? It's not the H2O. It's the sodium that's losing electrons. It's going from Na to Na+. So it's losing an electron. So our anode is the sodium here. So sodium is our anode. We can do negative 0.83. The H2O is going to be our cathode. Minus negative 2.71. So that's going to be the same as 2.71 minus 0.83. We get a value of 1.88. That's one way of doing it. The other way of doing it is we've got H2O going to H2 and OH minus. That's the direction that we've got it written in our underlined in green. So that one's going to be negative 0.83. Our other one, sodium going to sodium plus, is below it, and it's flipped. Since it's flipped, we just change the sign on the 2.71. So it's positive 2.71 plus negative 0.83. That'll do the same thing as this equation that we went through. So we flipped one, we add them together, you'll still get 1.88. That's the way that I would probably do it. I just thought it might be fun to show you the equation way of doing it. Questions about that so far? All right, so that gives us this standard cell potential. F is a constant, so we don't need to worry about that. We've got it up here. What is N in this case? Yeah, so N is the coefficient on our electrons. We don't have electrons showing up in our equation, so we have to figure out how many electrons are being transferred. If we look at our sodium equation has 1 electron in it. We've got coefficients of 2 on our sodium, though, as opposed to the 1 on our sodium in our half reaction. So that means that we've doubled it, so that would be 2 electrons. Or we could look at our H2O half reaction. Our H2O one, the coefficients are the same. for everything that's not electrons, so that means we'd have a coefficient of 2 on our electrons. So coefficient on electrons is 2.
If they're not the same, we have to match them there.
If you're putting it together yourself, you would have to get them to balance out, yeah. All right, so we've got stuff to plug into our equation. Negative coefficient of electrons, 2, and then a Faraday's constant, 96,485 coulombs per mole of electrons. And then our standard cell potential in volts, which is 1.88 volts, because our standard cell potentials are in volts. Okay, so negative 2 times 96,485 times 1.88, negative 362,783.6 units. What are the units? We've got volts times coulombs. It's joules. Volts is joules per coulomb. So if you multiply volts, which is joules per coulomb, by coulombs, the coulombs cancel. So it's left in joules. The other way you'd know is Gibbs free energy is in joules, typically. Okay, so we calculated our standard change in free energy for the reaction. Is the reaction spontaneous? Yes, the reaction is spontaneous. We've got a negative delta G. So yes, spontaneous. We've got a negative delta G. We also have a positive cell potential. Those are both signs that it's spontaneous. Questions before we wrap up?
Is there ever a case where they would be opposite situations?
They should never be opposites. So it's always going to be it's spontaneous for both or it's non-spontaneous for both.
Okay.
Should. All right, that'll do it.